Hey everyone! In Physics 40S world, it's Dr. Carroll here with Unit 4, Lecture 1. Unit 4 is all about taking mass and velocity and putting it together. In other words, momentum, and we're going to be focusing on linear momentum. There's another momentum called angular momentum, which you'll get into in your next course, but we're going to focus on linear momentum where a vector quantity is used and linear momentum is the product of the mass of an object and the velocity of the object. We will also look in this chapter at impulse, because impulse is related to momentum. I'm going to use capital J for impulse. Some people use capital I, but others say that's confusing with that because then they say, well, that could also be used for inertia. So I'll use capital J. Some people use a script J for that, and J is in fact the change in momentum. The units for both of these are kilograms meters per second. So you think by now the physicists would come up with, there's lots of great physicists out there, they'd have come up with a name so you don't say kilogram meters per second. But for reasons nobody knows, there are no one name units for momentum, so we'll always use kilogram meters per second. Often you think of momentum as in an election. Oh, this candidate's got the momentum. Lots of people are going to vote for the candidate. Or the Jets are winning lots of games, so they got the momentum now. And it gets all blurred, but here's the definition in a box. The momentum of an object, I'm looking at the mini text by the way, momentum of an object is changed when an unbalanced force is applied over a given period of time. The resulting change occurs in the direction of the force. So that is really what Newton had to say, and here's my equation. The momentum is the mass times the velocity. So you could have the same momentum for, let's talk about football, a large fullback who doesn't run that fast versus a less massive halfback who runs a lot faster, and they could both have the same momentum. So that's what actually example 1 has. Now whether I'm looking at the mini text or the our booklet, I'm looking at the same question. So I'll dance back and forth between these two, and you're getting used to that now. So let's say you have a 1 kilogram duck moving at 28 meters per second. So here is this duck. Oh, that's a fast duck. In fact, a biotech super performance duck. Fine. And there's a sumo wrestler. We saw this sumo wrestler earlier in this course, didn't we, with the gymnast and force of gravity. Anyways, the sumo wrestler has a mass of 200 kilograms. Wow. Moving at 0.5 kilometers per hour, you divide by 3.6, so that's 0.14 meters per second. You want to calculate the momentum of both. So there's the duck data and the sumo wrestler data, and the momentum of the duck is the mass of the duck, 1 kilogram, times the speed, 28 meters per second, so 28 kilogram meters per second. So that is the momentum of the duck. The sumo wrestler is 200 kilograms times 0.14 meters per second, so also 28 kilogram meters per second. So the duck and the sumo wrestler are both going at the same momentum. Okay? Someone asks you if you'd rather be hit by a piece of chalk or tackled by a serious football player. You might say, oh, you'd rather be hit by the chalk. But if the chalk was moving at 250 meters per second, then it's like it's a bullet. So you'd rather be hit by the football player. Fine. Okay, so here's some questions here. 100 kilogram football player at 12 kilometers per hour. Blue whale, 150 ton. A metric ton is 1,000 kilograms. You don't have to memorize that. Moving at 30 kilometers per hour. That's going to have more momentum. And then a rocket, well, that's going to have even more momentum. And I have those calculations here. So there is the football player, the 100 times 3.33, 333 kilograms meters per second. The someone mowing their lawn somewhere. Momentum of their lawn. We have here the 150,000 kilograms. Which one was this? Was this the whale? Yeah, the whale, the blue whale. So times 8.33. So it's traveling faster and it's much more massive. So look at that momentum. 1.25 million kilogram meters per second. And then the rocket, well, a heck of a lot more. Okay? Then let's look, how does momentum relate to Newton's first law? Well, it's really Newton's second law that we talk about change in momentum. I guess if your velocity isn't changing, then neither is your momentum, right? Remember, momentum is mass times velocity. So if your velocity doesn't change, neither does your momentum. Momentum stays constant. It's the change in momentum, which is when we talk about impulse, acceleration, all that other good stuff. So remember from Newton's second law, F equals ma, but acceleration is delta v over delta t. If we assume that mass is constant, then we can write that as delta p over delta t. So the change in momentum with respect to time is force. If I multiply both sides, I get delta p equals F delta t. And that is the definition of impulse, the change in momentum, which is F delta t. So we can also write it if delta p is m delta v. So F delta t equals m delta v equals j. Okay, and again, we aren't going to assume that the mass is changing. So this is actually a discussion of cause and effect. An object just sitting around minding its own business has a force applied to it for a period of time. So that is now the cause. The object moved and its velocity changes. The velocity changes, so does momentum. This is the effect. And it's easier to see the effect side of the action rather than the cause side. The left side of the equation is called the impulse, kilograms meters per second, or Newton's times seconds. Gives you the same unit. And the right side is the change in momentum. So you impart an impulse to create a change in momentum. If you don't believe me that Newton times seconds is kilogram meters per second, remember a Newton, 1 Newton is 1 kilogram meter per second squared, and I multiply by units of seconds, so I get 1 Newton times seconds. 1 Newton second is 1 kilogram meter per second. Okay? So we have an impulse from a club, and it changes the momentum of the golf ball. We can perform calculations using the magnitudes only, but we should be conscious if there is a direction change during a question. So let's see how this all works. Lots of sports examples here. Golfer hits a ball of 45 grams, immediately convert that to kilograms. So 0.045 kilograms, and it leaves the tee at 40 meters per second. So the golf ball's on a tee, and its initial velocity, v1, is 0 meters per second, and v2 is 40 meters per second. So we're hitting the golf ball, and therefore an impulse is being imparted by the golf club to the ball, and a momentum is changed. So what do we want to find? The impulse. So F delta t, which is m delta v. So just 0.045 times 40 minus 0. Okay, so we don't know the force, we don't know delta t, but we do know the other way to write it, so it's m delta v. So it's m times 0.045 times 40 minus 0, or 1.8 kilogram meters per second. Therefore, the impulse is also 1.8 Newton times seconds. The sign of the velocity and the sign of the impulse are the same. The direction of the impulse was acting in the direction of the golf swing. In sports involving something hitting a projectile, we watch the effect part of the equation. If we were to watch the impulse part, our eyes would need to see and interpret events much faster than they can. You need to see things in milliseconds, so you're actually looking at the effect. And often it's subtle. When a goalie catches a puck or an outfielder catches a ball, the gloves do more than protect the handle and provide a larger catching surface. The glove is made of a soft material with webbing stitched into the catching part of the glove. When the puck or ball hits the glove, it's cushioned and brought to rest. Right? So you move your hand back a little bit, so you are stopping things, so the change in momentum happens, but you're cradling the baseball, whatever it is, and in so doing, your force felt by your hand is less because the time of catching is more, right? So your change in momentum is smaller force if you have a larger time. And that's what in sports you're taught that, right? To cradle the football, basketball, whatever. So leather is used for baseball. So flowcharts, yeah. I'm not big into the flowcharts. You can look at them if you want. If they help you, use them, right? So we see here that the wooden glove is going to not work as well as a leather glove. See, here's a hockey player cradling the puck. Now, you don't want to put your glove back too far because then it's going to go over the crease and they're going to score a goal. So before I do example 3, let's see if there's anything else to say here. There's our golf ball. Okay, now we get to the parachutist. So this is like, and again, sports people know this, when you're landing, you bend your knees, right? So let's say a parachutist lands, flexes her knees, and rolls in order to stop. Calculate the impact force on a 70-kilogram parachutist falling at 10 meters per second if the time to stop was 0.8 seconds, and then repeat it where you aren't doing all this rolling and you're just trying to stay rigid as you standing at attention as you land, and so you want to stop in much shorter time. Here, just 0.05 seconds. Well, that's going to be harder on your knees. That's going to be a tougher force. You might break your knees. So for the first case, 70 kilograms, we start at 10 meters per second, we go to 0. It took 0.8 seconds. So 70 kilograms times you stop. They want to know the impact force once you've stopped. So 70 times 0 minus 10, all divided by 0.8. So the force that your knees feel is minus 875 newtons. For the stiff-legged case, 70, same mass, 0 minus 10, but you're stopping in just 5/100ths of a second. So that is 14,000 newtons. Okay? And the negative sign means that the stopping action is in the opposite direction to the initial velocity. Just for that small change, that 3/4 of a second, the force is increased by, what's that, 14,000 minus 875. 13,125 newtons. That is enough to cause a serious injury. Okay, so if any of you ever do any parachuting, I doubt I ever will, but if any of you do, now you know a bit more about it. Okay, sometimes you want to have a small interaction force and a small interaction time and a high interaction force. Like here, I'm hitting a hammer, so the time is small. I'm changing the momentum of the nail. The time is small, the force is great. Sometimes I'm talking about a smaller force. Okay, and that's going to be, okay, so the change in momentum, so smaller force, greater time, and so we'll get still a change, the same change in momentum. So you sometimes want to be more in control in terms of force and sometimes in terms of time. Okay, let's go here. These examples are, shall we try them out? Why not? Where are they here? 281, number 4, number 5. 281, number 4 and 5. So let's go to the mini text here. And let me find a page number here. 281, it said? Let's go back here. Scroll up. Sometimes you get the numbers mixed up. They mean 291. No, that's a different thing. Okay, let's just look at these ones here. Let's say we had this may be from it. Well, I'll just work it out with you here. Let's say you have a mass of 20 kilograms. You have initial speed of 0 meters per second, and then the speed goes up to 3 meters per second. So my change in momentum is m delta v. If you're asked to calculate that, which is the impulse. So it's 20 times 3 minus 0, which is going to be 60 kilogram meters per second. Okay, so that is my momentum. If you started at 0 and went to 3. If you I think this one you're just reversing the direction. So it's minus 60, and the third one is you start at 3 and go to reverse to minus 3, so you get greater with the direction change. Okay, 5 I'm not going to do right now. Okay, so I will find you a worksheet. Don't worry, I'll find you a worksheet for those momentum ones, and we'll do more of them. But let's spend the rest of this class looking at the law of conservation of momentum, because momentum is conserved. That means in your system, whatever momentum you have at the beginning is going to be the same as the momentum at the end. So if you had just two bodies, you could have like body 1 and body 2, and I'll use initial and final. So m1 v1 initial plus m2 v2 initial, there's my vectors, equals m1 v1 final plus m2 v2 final. Or p1 initial plus p2 initial equals p1 final plus p2 final. Okay, so that's conservation of momentum. Let's start by looking at it in just one dimension. So this one here, example 5, involves some hockey players. I don't want to do 2 dimensions yet. Got to start with 1 dimension before we go to 2, right? So we have here 2 hockey players, Ottawa and Montreal, and calculating momentum of objects initially at rest. These are recoil, right? You can have a recoil. So they're both at rest at the beginning, and the Montreal player pushes the Senators player one way, so then the Montreal player goes back, let's say to the left, and the Senators player goes back to the right. Find the velocity of the Senator if the Canadian moves back at 10 kilometers per hour after the push. Okay? So we have a 90 kilogram and a 105 kilogram. They're both at 0. The first player pushes back one way, 10 kilometers per hour, or 2.8 meters per second. The other one, we want to find that. So conservation of momentum gives the first player isn't moving, the second player is not moving, so they're both 0. And then after the one player is moving back, so it's 90 times minus 2.8, and we want to get the velocity of the other player. So we bring the 90 times 2.8 onto the other side, divide by 105, and it's 2.4 meters per second. So the Senator moves to the right at 2.4 meters per second. The Canadian moves to the left at 2.8 meters per second. But the Canadian was less massive than the Senator, so momentum will be conserved. And here you see it. The total original, here this book uses original or initial momentum is 0, and the final momentum, the original momentum is equal to the final momentum equals 0. That's right. Yeah, obviously the original momentum is 0 because neither of them are moving, right? The final momentum is minus 252 kilogram meters per second for the Canadian and positive 252 kilogram meters per second for the Senator, so it adds up to 0. This example shows that you must be careful not to automatically assume there is no motion when the total momentum is 0. Here there is still motion, they're just one's skating backwards, one's skating forwards, one's faster than the other, but one's more massive than the other. Here's an example where you got rugby players. You want to calculate the initial velocity of the American rugby player if she tackles a stationary, that means not moving, Canadian player, causing both of them to move off with a velocity of 1.4 meters per second. I see kilometers per hour, divide by 3.6, and I get 1.4 meters per second. Both rugby players have a mass of 75 kilograms. So we're going to calculate the initial velocity. So the American is going to be 1 and the Canadian is going to be 2. So M1 V1 original plus M2 V2 original is M1 V1 final plus M2 V2 final. So the American's going at 75 with an initial speed we don't know of, and the Canadian's going at 75 times 0, so just 0, fine. After, they're both going at the same speed, 1.4 meters per second, which means that the American must have had an initial speed of 2.8 meters per second. You can see that that makes sense, right? Because they're both the same mass, and the American's coming in at twice the final speed, because that, if you even want to think of it as energy, it's being distributed into the two same mass objects, so the initial speed had to be 2.8 meters per second. Okay, example 6 shows a collision where the two bodies join and don't become one body, right? Okay, same here. You have a car crashes where the cars don't spring apart. See that in demolition derbies all the time is another example of that. So those are examples of one dimension. Let me do another one-dimensional one, and then in our next lecture, we'll look at two-dimensional momenta. Here's a recoil one. Let's say we have a bullet of mass 0.03 kilograms leaves a gun at 1,000 meters per second. If the gun mass is 1.5 kilograms, what is the recoil velocity of the gun? So let's assume initially that the gun isn't moving, and then after I want to find the velocity of the gun. If the gun is 2 and the bullet is 1, then V2 final is minus M1 V1 final. So the bullet was 0.03. The final speed of the bullet is 1,000, and the mass of the gun is 1.5. So you get the gun going at 20 meters per second going back. Some are going to say, well, is that the gun's mass loaded or unloaded? It doesn't say here, but you can see how that would really not make much of a difference. Some people, I guess, at rifle ranges will wear some sort of padding so that it won't hurt their shoulder when there's a recoil. Okay? If you do want to talk about the loading and unloading, here's, let's say the gun recoils at 2 meters per second. The unloaded gun mass is 2 kilograms. The bullet is 0.01 kilograms or 10 grams. What speed did the bullet exit? So again, set it up, assuming that originally there is no motion. I mean, you could be like in like some James Bond movie, be running with the gun, but let's just assume not. So 0. So I want to solve for, here I've decided that the gun will be 1 and the bullet will be 2. So the final velocity, V2 final, is minus M1 V1 final of M2. So minus 2 times you're going back, recoiling, so that's why I put a negative 2 there. And then the mass of the gun is, of the bullet is 0.01 kilograms, so I get 400 meters per second. So obviously the bullet is going to be traveling a lot faster than the gun. But this is all part of conservation of momentum. Here's another example of one-dimensional cases. This is a coupling example, and that's the word they use. A coupler is like those hooks that come together when the train cars hook into each other. So you could have one train car 40,000 kilograms, another one 35,000, and suppose the second train car isn't moving. The first one's coming in, so let's find what the final velocity is of the super train, right? So m1 v1 initial plus m2 v2 initial equals m v final. So 40,000 times 48 plus 35,000 times 0, so just 0, is going to be 75,000 times v2 final. So 40,000 times 48 divided by 75,000 is 25.6 meters per second. So the second object is going to be traveling at 25.6 meters per second. But when I think about it, that's not the second object. That is the combined object, right? The mass final is m1 plus m2. So it's 40,000 plus 35,000. So it's 75,000. So v2 final is 40,000 times 48 over 75,000, or 25.6 meters per second. And you could have a case, well, what instead if we had the second train car moving towards the first one? So they were both moving initially. So I want to get v2 final. So that's going to be m1 v1 initial plus m2 v2 initial over m, right? So 40,000 times 48, but instead of 0 here, it's 35,000 times minus 50. All divided by, they couple together, mass is still 75,000. So you see here that it's just 2.27. Now is that positive or negative? Let's punch it out here. I think it's positive. 40,000 times 48 plus 35,000 times 50 negative, all divided by 75,000, and I get 2.27, right? Positive, that's positive 2.27 meters per second. So that's a lot smaller than 25.6 meters per second, but that's because we're having train car number 2 going towards train car number 1. It's not stationary, it's not going in the same direction as 1, it's going in the opposite. So they smash together, noisy interaction, and our result is still a little bit positive. Okay, 3-point explosions, that is two-dimensional style of question, and I will get to that in our next lecture. Okay, so there'll be some worksheets and things for you to practice on momentum, change in momentum, impulse, and one-dimensional interactions involving the conservation of momentum. Momentum is conserved. Okay, have fun.